Hi everyone, today I'm going to be solving the chemistry AMS for week 10. So our first question is, which of the following conditions refer to standard temperature and pressure, STP? So when we're talking about standard temperature and pressure, it's a question based on our knowledge. Just remember that it's always pressure of 1 atmosphere and a temperature of 0 degrees Celsius. Next one requires solving. So aluminum reacts, they give us a nice chemical equation. This one's balanced. If it's not balanced, guys, make sure to balance it or you're going to get a completely wrong answer. So sample of 108 kilograms of aluminum reacted with excess of oxygen gas to produce aluminum oxide. So part A, find the number of moles of aluminum in the given example. So we're going to use the formula N is equal to M over M, where N is the number of moles, the small m is mass, and the capital M is molar mass. So we know our mass is 108 kilograms over 27, which is our molar mass, which gives us 4 moles of aluminum. Now, we need to calculate the number of moles of oxygen consumed by the reaction. So here we're going to be using the stoichiometric ratio. So before we're going to write an equation to solve this. So on the first thing that we do, we identify what is already known. We know the number of moles of aluminum, so just write them down. Now, we need to multiply this by the stoichiometric ratio. We're going to identify it right now. So what we're trying to find is the number of moles of oxygen gas. So it's going to be 3 moles of oxygen gas because that's what we're trying to find. So it's mentioned over here. Now, at the bottom, we're trying to find, again, our known, which is 4 moles of aluminum. We can cancel them out because they're clearly the same. We're left with 3 moles of oxygen. In this case, in this question particularly, the number of moles in the balanced reaction is the same, but when we're going to have a different stoichiometric ratio, when we're going to convert not just moles to moles, but moles to mass, or mass to moles, which requires 2 steps, or mass to mass, which requires 3 steps and is one of the most complex basic stoichiometry ratio questions, we're going to need the stoichiometry ratio and the equation that I just showed you more, and it's just like the first, like the beginning of stoichiometry in this question that we saw. So now we have the same that we need to calculate the mass. So we're going to be using the same equation of mass over molar mass. Our mass is still 100. Oh, sorry, we don't know the mass. So we know the number of moles, which is 3 that we found earlier. We need to times that by our molar mass, which is 16 times 2, because over here we have the prefix of 2, so that's 30. So we're getting the answer of 96.00 kilograms. Now, we need to write a balanced chemical equation first. So sodium metal, which is Na, that's a solid, plus excess water. We know that water is H2O. H2O, it's considered a liquid, of course, obviously. NaOH, which is one of the results of our reaction, is aqueous, plus H2. We have a small problem here of the fact that the equation isn't balanced. We can't start solving anything. So let me just balance it like really quickly. 2 over here, 2 over here, and 2 over here. So we need to find the number of moles of sodium metal that reacted. So here we can use the same formula that we used earlier, which is N equal to M over M. Our grams is 4.6. Our mass is 23. And that gives us 0.2. That's how we find it. Now, next one will also require the ratio part. So we're going to write first what is known. What is known is 0.2 moles, that we have 0.2 moles, times our stoichiometric ratio. What we're trying to find is the number of moles in H2. So the prefix of moles over here is 1, right? So for 2 moles of Na, we're going to have 1 mole of H2. So 1 mole of H2. Sorry, I forgot to mention that this one's Na. And obviously at the bottom, we're going to have 2 Na as well. Because here, the prefix is Na. 2. So we're going to cross out the Na so we can do the calculation. Now 0.2, we just times by 1 over 2, which gives us 0.1. Now, zinc reacts with hydrochloric acid and releases a hydrogen gas according to the following chemical equation. They gave us the equation, thank God it's balanced. A student added 0.109 grams of zinc granules, blah, blah, blah. We don't really need it for now. Make sure to read the question in the exam. Okay, so we need to calculate the number of moles in zinc granules consumed in the reaction. So here we're obviously going to be using the same formula that we've used before. N is equal to mass over molar mass. So 0.109 grams is going to react with, okay, molar mass is 65.4. It's given over here. If it's not, use the periodic table. Okay, so we're going to get 1.67 times 10 to the negative 3. You just do the math. I'm not going to really waste time. 67 times 10 to the negative 3. Now, there is a small trick. Of course, you can do the same thing for hydrogen, find the molar mass, but whatever. Let's use the stoichiometric ratio instead. So we can see that for 1 mole of zinc, for 1 molecule of it, we're going to have the same amount of hydrogen. So see, there is no coefficient next to the 2 elements, right? So we can estimate, and we know that if it's a 1-to-1, then the number of moles produced in the zinc is going to be the exact same as in hydrogen. So it's also going to be 1.67 times 10 to the negative 3. Next one. So we're trying to locate the syringe indicating the total volume of hydrogen released RTP conditions. So in the first question, we had STP conditions, and that's 22.4. But here, our molar volume is 24 decimeter cubed moles inverse. So let's use the basic formula that we had, which is N. Now it's V over Vm, which V indicates volume and Vm is molar volume. We know our molar volume, which is 24. Our number of moles is 1.67 times 10 to the negative 3 over 1. So we can do the cross multiplication. And let V stay the same because that's what we're trying to figure out. And here we're going to have 24. So we cross multiply that. Oh, and by the way, it's decimeter cubed. So we can cancel out the 10 and decimeter. So at the end, we're getting an answer of approximately 40.08. Now let's see what is suiting us the best. Here it's 10. So definitely that's not corresponding to 40.08. Same here, it's like 22.5 approximately, wrong. And the last one, which we have, is 40.08, pretty much what we're looking for. Wonderful. And the last one also doesn't suit us because it's like around 36. So you're just trying to find out the volume, and based on that, you look at the syringe that indicates the number that you found. Now, a sample of 0.500 mole of butane gas undergoes complete combustion at RTP conditions according to the following chemical equation. Also balanced, wonderful. So we're trying to find the number of moles of oxygen gas. So here we're going to be using the stoichiometric ratio. So our known here is 0.5 moles, right? That's what we know. So, sorry, that's butane gas. So that's C4H10. Make sure to say that it's C4H10 or whatever other element you have, just so you know what to cancel or not. So here it's going to be our stoichiometric ratio. So what we're trying to find is oxygen gas, right? So that's going to be 13 of O2. Over here we have 13, right? So at the bottom, we're going to be having something related to C4H10 as well, which is the number over here. So our stoichiometric ratio, so C2C4H10. We can cancel out the C4H10. We're left with this equation. We do the math, use your calculator, and this is gonna give us 3.25 moles of CO2. That's what we're trying. Oh, sorry, it's not CO2, it's O2. But anyways, we've got the answer. So 3.25 CO2. Now we need to find the volume of oxygen needed to react completely. So we could have thought that we also need to use the stoichiometric ratio, but not for this one. We have the equation that we had earlier, which is N equals to V over Vm. We're trying to find the volume of oxygen. So we know that our moles is 3.25 over 1. Let this one be still V because we don't know it, and we have RTP conditions, so 24 decimeter cubed. We cross multiply. That gives us 78.0 decimeter cubed. That's pretty much it for this question. Again, make sure to write the correct number of significant figures. Now, we have percentage. As we know, percent basically, in this case, it's 20 over 100, because that's how percent is calculated. And cross out the zeros, we're left with 0.2. So forget about the 20% of oxygen gas over there. You have the 0.2. That's what you're going to be using. So to find the volume of air, we can still use the volume of oxygen, which we found just over here, over the percentage, so over 0.2. So it's going to be 78 over 0.2, which gives us 390. And pretty much it. We just write that down. Okay, and that's it. We move to the next question. Now, we need to write a balanced chemical equation for the above reaction. So let's write the unbalanced chemical equation, so it's going to be easier for us to understand what are we missing. Cl3, and I completely forgot the 2 over here. Now, if we have 3Cl and 2Cl over here, the Cl has to be balanced, no? So the common factor that they have between them is 6. So you can times this by 3 and times this by 2. But now we're faced with another problem. If the chlorine is balanced, the Cl isn't, the iron isn't balanced. So if it's 2 iron here, then it should be 2 iron over here. That's it. We balanced. You can check by just calculating the amount of each number of each element. So now we're going to be using still the stoichiometric ratio. No, sorry. Here it's. Oh. Yeah. I'm really sorry. We're still going to be using the stoichiometric ratio over here. So 6.0 moles. That's what we already know. That's what's given. So what we're trying to find. Sorry, that's CO3. So that's going to be. We're going to times that by the stoichiometric ratio. Which is basically, on top goes, again, what we don't know, what we're trying to find, so Cl. From our balanced chemical equation, we can see that it's 3Cl. On the bottom goes what we know, based on what is given. So if it's, so iron trichloride is given, we need to put the 2 iron trichloride to the bottom. Cancel out the trichloride. Now we're left with basic math. You use your calculator, and you're left with 9.0 moles of Cl2. Now, sodium reacts vigorously with chlorine gas to produce sodium chloride as shown in the following chemical equation. That one's also balanced. Now, in an experiment, 14.2 grams of chloride react completely with a given sample of sodium. Given atomic masses, okay, so find the number of moles of chlorine reacted. We can use the equation that I've showed earlier. N is equal to mass over molar mass. Our mass is 14.2 grams. Molar mass is 35.5 times 2, because over here we have a prefix of 2. That gives us 0.2. 3 significant figures. Now, we're trying to find the number of moles sodium chloride produces. So we're still going to be using the stoichiometric ratio. So 0.2 mole. That's what we know. That's Cl2. So Cl2. Now we look what we're trying to find. The sodium chloride, that's 2 NaCl over what we already have is 1 Cl2. Cross out this. Now we can cross multiply or whatever. So in this case we divide. So 0.20 or 200 we divide by 2. That gives us 0.1. So we're ending up with 0.1 over here. Now, we need to find the mass of sodium chloride produced. As long as we, it's 3 significant figures, so this as well. Oh my god, I'm really sorry. I did a mistake in calculations. I was right. You need to times that. So, from that equation, you get 0.400. Sorry, I just noticed that mistake. So, find the mass of sodium chloride produced. We're going to be finding the mass by multiplying number of moles times molar mass. So our mass is NaCl. So that's what we're trying to find. That's our molar mass. So 23 plus 35.5, because we know that the mass of reactants on one side and the mass of products on the other side is equal. So that gives us 58.5. That's how we found our molar mass. Because, so for NaCl, we need to find the mass, like the molar mass for NaCl fully. And then we're going to be dividing it, we're going to be timesing it, multiplying it by 0.4 that we found over here, which is the moles, which gives us 23.4. Okay, so liquid hydrogen peroxide decomposes into water. So let's write down H2O2. It's also balancing. They're asking also for symbols if it's liquid. Of course, liquid. It decomposes, so it's still a reaction into water, H2O. That's liquid as well, plus oxygen gas, which is a gas. Okay, this is not balanced. To balance it, we should check the number of hydrogen molecules on one side, on the other side. Here we don't have a 2, so we of course should add a 2 over here, but now it gets to 4, and in some there's also 4 atoms of oxygen, so here it's going to be 2. So we just balance it the way we check how many molecules of each element there is. Now, magnesium reacts with oxygen gas to produce magnesium oxide. So let's say that our O2 is what we're trying to find. If we know that 2 magnesium gives us, does it give us? So 4.8 over here and 8.0 over here. So we're just going to do 8.0 minus 4.8. That's just how it is. And that gives us 3.2. So we just figure out what is unknown, and then based on that, we make an algebraic equation, and that's it. Okay, so during a chemical reactions, atoms are conserved and the total mass of reactants is always equal to the total mass of products. Now, burning butane gas in air, that's a chemical reaction, chemical change. Grinding coal, that's physical. Dissolving, that's just a change of state, so still physical. Boiling water till it evaporates, that's physical change as well. And heating gaseous hydrogen-oxygen mixture until it pops, that's a chemical change. So anything that involves a change in state, that's considered just a physical reaction. But if we're producing a new substance, that's a chemical reaction. Now, a substance X undergoes a chemical change. I've just spoke about it, that we're gonna have a new substance. So a form of substance, a substance X changed into a new substance Z. So something new is produced in a chemical reaction. Now, which of the following are balanced chemical equations? So again, we should count the number of molecules on one side of a particular element and on the other side. So this one seems correct. I mean, fractions aren't really used, so we can just like times that by 2, so everything becomes with whole numbers, but apparently it still works. And then 2H2 and O2, that gives us 2H2O, also suits us perfectly. So it produces a new substance, that's a chemical change. Great heat change, also chemical change, does not produce. Physical and is just a change in form, physical change. So we can go back. Now, number 15, which of the following are combustion reactions? So burning wood, and combustion reaction is also a chemical change. So reaction of methane with oxygen gas and the reaction of fuel with oxygen gas is all chemical reactions. Now, here we need to apply the conservation of atoms. So if we know that we have 30 molecules of water, we need to find the number of molecules of oxygen. We can see that it's 2 of them. So we're going to be dividing 30 by 2, which gives us 15. And over here, it's still going to stay 30. It's still going to stay 30 because we're still going to be using the same amount of hydrogen. Okay, number 17. Read the following molecules, complete the sentence using numbers. So what we need to do here is, as long as the equation is balanced, we need to just see the coefficient next to N2, to 3, hydrogen 2, and so we're going to be just doing 1, 2, 3, and 2, as long as the equation is balanced. So 1, 2, 3, and 2. So here in number 18, we're going to be calculating the number of, we're going to be calculating the molar mass. So our grams in N2, because we have the prefix over here, it's 2. We're going to be multiplying it by 2. So 14 times 2, that gives us 28. of N2. So that's going to be our first answer. Now, based on that, we do the exact same thing with H2, but there we need to multiply 3 times 2. So if we have something before, we need to multiply it as well with the, so we multiply the coefficient with the prefix. So we know that H is 1, so 1 times 6 gives us 6 of H2, 6 grams of H2. Now, not to calculate the whole thing for NH3, we can just add up 28 plus 6, which will give us 34, because as we know from the rule, the mass of reactants is always equal to the mass of products, the total mass of reactants. So 1 mole at STP is 22.4. It's a rule. Now here we just so we're trying to find the following balance equation STP. So ratio of reactants. So 2, because look, if it's a gas, we look at the coefficient next to the compound or mixture, and we just write it down. So 7, here's going to be 4. But if it's liquid or solid, it's negligible. So there is no volume, so we just put 0. Next one. So we balance the equation first. Based on that, we can see that we have 3 over here for x. Actually, to make your life easier, try balancing oxygen as the last thing. So leave it until the very, very end. But I balanced it first though. Y in this case is going to be 2. Because from here we see that we have 2 of oxygen. So here should be 2 of oxygen as well. And 2 of carbon as well as here. And then Z we have 4. Same thing. So now ratio by mass. We're going to be calculating it by number of moles over molar volume. Just apply the formula here, M over M. That's how we're going to get the mass. And just write the mass for each of the following, which we start off by 64, 96, 88, and 72. Now, total mass of reactants is equal to total mass of products. So basically we add this up. So the same thing is going to be here. It's both going to be equal. So if you put on your calculator 64 plus 96, we get 160. Of course, by the rule, the total mass of reactants is equal to total mass of products. So it's equal to, so it's conserved. So that's pretty much it for this AMS. Thank you so much for your attention. Good luck on Monday.